Today is 18th of September 2025 about big data. Today what we did is first, what is the parallelism? After parallelism, we're talking about yeah, just parallelism. When designing the parallelism, what we do is making from sequential version. And this is the basic constraint of physical work, and then we will make parallelization. Then what we should think about is there is always overhead because you should check the combination and you should distribute it. Then we will calculate the numerical complexity, and then we will check the efficiency and scalability. When you basically what we'll do is code analysis. When we do code analysis, in compiler level, we need to check symbolical and the other stuff, and if we will check GDP things. And if you go to CUDA level, then I should just check is how many streams multiprocess, bank, and main function has, and how many input metrics from PCI to how to distribute it, and so on. When you calculate execution time, there's CPU time plus IO time and system time. IO time is basically memory operation like malloc, and CPU time. Uh, and system time is uncontrollable. And when you do IO, there can be context switching and OS caching and cache allocation, and eviction will be happen. This is uncontrollable. So basically, how can you check the time? Then how can you check the time? There can be a lot of tools such as NVProof or uh, that is all visualization tool. But I don't think it actually needed like function called start to end. But if you just use import and checking the time, then you'll be able to use it. So maybe we can do such experiments like doing either C++, Haskell, and Rust and Python. You can try it, of course. And in parallel time, there is parallel overhead happens, which is parallel time equals to computation time, we saw below. Plus, there will be additional time, which is plus, there will be, no. Plus coordination plus idle time, which will be communication plus synchronization, and the different one, load balancing plus sequential selection would be the one that we should actually care about it. Hmm. So, in communication overhead situation, type of communication we should consider is memory sharing or message passing. Memory sharing is basically access to shared memory space, so it's more easy to communicate. But message passing, in that case, we should like check whether whether other call is possible or impossible. Uh, so in memory sharing case, overlap memory request with other instruction if there is enough work to do, and message passing in that case, being sent, initiate the RECB. RECB. Yeah. If you have done the C++, then you will not solve this. RECB is. Yeah, so on. And latency and bandwidth. And if you actually want to super increase the latency and bandwidth, the most simplest way would be, wait a minute. There's OS level, kernel level, device module, and Linux schedule changing. If we change this one, then we can when we talked about the system time, we can change the system time. But except that case, we can't handle the system time, and we can just handle the CPU time. So and then yeah, shared memory, shared folder in this case, it is like surely shared folder. Think of that the window. There's bit format address, and in shared memory case, there's lock, mutex, async, and synchronize. This is also connected with later problem. How should we assign the code, sequential code to multi-core? Then there's option of process and thread. The biggest difference is process not sharing the state and memory. Thread shares memory and space. That state, that is the biggest difference. To increase the latency, the most good thing is memory sharing. For if we only consider the latency, what we can do is actually memory sharing and doing the polling with while loop. that it will be the most the efficient way. But we not only consider this one, this will be uh, cause another problem. And mm, also, yeah, there's another example like linked list. There's next pref, the next pref pointer. You will usually use it, and when change happen, when the printer change, and if interrupt happen, then what happens? We need to consider whether whether the log operation and so on. And when linked list not updated in register, there's L1, L2, L3. If you go far back behind, it needs more cycle, 200 cycles. Then when we are going to print it, even register or L1 cache, L2 cache, L3 cache, they all need to guarantee that they have same value. Then how can we do it? This is kind of problem issue. Map multiplication also, if row is not fit within L1 cache, then how should we put it? In L2 cache, in L2, L3 cache, that is another problem issue. Spin lock in Linux kernel, expectation of lock versus unlock. Then we use spin lock. That's how it is implemented in Linux kernel. And asking relentlessly, can we receive? And mutex is, can we receive and wait for 5 seconds as mutex? And there's a point come up, a very important point, which is granularity, uh, computation to communication ratio. So basically, you can, uh, I would say it's uh, fine versus courses. You can split everything and put it, then a lot of communication happen. 1 bit multiplied by 1,000, or put 1,000 byte and just 1 second. In coarse case, load imbalance happens, and previous case, communication synchronization issue is dominated. So we can also call it as computation communication ratio, 1 byte, yeah, fine grained versus coarse grained. For latency, it will be, of course, just send 1 byte. It's for uh, very many times will be better. So parallelism, this now parallelism comes arise. Parallelism is basically one node and there is multiple core. Each core has its cache connected by bus and backed by shared memory. So this is kind of well fit with machine learning because it pixel level, it fine-grained it with large scale. But in from 2 nanometers, there's another problem happens, which is in between cores, it can't distinguish between 0 and 1, even without we control it, but content tunneling happens. How to split code to multi-cores is so issue. So we can use process and thread to explicitly split into multi-cores, while schedules and process on thread level mapping to core. Process has its own memory space. Thread shares the same memory space as the core thing. Rust tries to do synchronization and ordering, but it's not, I would say it's not easy peasy thing. And also uh, frequency concept come up, which is computational power per 1 second. Unexpected delay can happen, which is when you write as planned, then it's done. But if cache miss happens, then it needs to go to the lower level caches from L1 to L2. And if we go further, page first happen, then it could be maybe 10,000 cycle happens. And if it goes more, then we should go to SSD. Then it's not just cycle unit. This is very unexpected delay. Then we should care about it when we compute it. And also scheduling quantum happen, then this kind of thing is not easy to handle, then we need to consider about how to handle those stuff. These are the kind of things what we should consider. Mm, yeah. Code analysis. Yeah, those are the things that we should consider. Mm, shared memory space. We can use polling. That what we talked about. Okay. Thank you very much for today.